Right. Okay. So we were doing a problem last time. We finished a problem, and we're going to do another one. But before I continue from here, is there any question from the previous lecture concerning the problem or any conceptual thing? Any question? I remember this. No questions. Okay. All right. Let's do another problem. I don't know what is this thing doing. Okay. Okay. I'll write down another problem. Let's model it. We have an object, and it's thrown upwards. So let's suppose that the object is a ball, and it is thrown upwards. Right. Suppose that this is the ground, and it's launched upwards from the ground, and it's launched with some velocity of, suppose it's 15 meters per second. So this is the velocity with which the ball is launched. So I use the symbol U because this is the initial velocity of the ball with which it is thrown upwards. Again, assume that air resistance is negligible or zero. The first thing is, with this information, determine the maximum height that the ball can reach. So how do we do that? Any ideas? So well, if the other information that we naturally have is that there is a acceleration due to gravity, which is acting downwards of 9.81 meters per second squared. Right. So really you have U, you have the acceleration A, you want the maximum height S that can be reached. There is one piece of information that is also specified, but it is hidden inside your question, and it is in the statement that you want to find the maximum height that the ball can reach. So can you take a guess? What information is this statement giving me regarding one of the physical observables? As in, could be
final velocity is 0 at maximum height.
Final velocity is 0 at maximum height. Exactly, right? And again, a very simple reason for that is if it's going up, suppose if it's positive going up, then you can only differentiate the downward motion by attaching a negative sign to that value. And so, of course, if you're going from positive to negative, you're crossing a 0. So the height, the velocity at one point must be 0 to change its direction. So whenever there is a change in direction, the velocities always crosses a 0. So exactly. So the final velocity is also given as 0. And so let's write it like this. And S is to be determined. How can I do this now? How can I find S by using these variables?
Sir, we are going to use the equations of motion. 2as is equal to mu squared.
Exactly, right? So yes, so we'll use the final velocity squared minus initial velocity squared is 2as. In this one, you have this, we have this, and this. All the variables are known, as in S is to be determined, but so we can just factor it out. So S is just v squared minus u squared divided by 2a, right? And this, doing the math, this one is 0, the velocity that it's going upward, the maximum final velocity 0 squared minus the initial velocity with which the ball is launched is 15. So 15 squared divided by 2 times acceleration of gravity. So the upwards velocity is taken as positive 15, right, in this thing. So downwards gravity should be minus 9.81, because you have set the scale for the system by taking a positive velocity, positive 15. You have set this thing that the upwards direction has a positive signature attached to it, which will automatically mean that a downward direction should have a negative. So gravity is downwards. That's why it has a negative sign with it, negative 9.8. So this math just gives you 11.5 meters. So is that clear?
Yes, sir.
All right. Okay. Let's do another part for this. Okay, so we have the maximum height. What else can we find? We can find, let's say that you want to find how long it takes to reach this maximum height, right? So time to reach max height, right? What is that? Again, how would we do this? Any suggestions? So what do we have? We have initial velocity, we have acceleration, we have the maximum height that we are talking about, we have the final velocity as well, and we want time, right? So time is unknown and these variables are known. So what can we use to figure out time?
Sir, S is
We have
equal to
we can use S is equal to ut plus half at squared, but in this case we have t squared as well, so we have a quadratic term in t. This equation is quadratic in t, so of course you can use this equation and solve your get an answer for your thing, but it's much more easier to use another equation, that is v is equal to u plus at. Even in this equation, you know all the variables, right? You know v, you know u, you know a, and t can be figured out. You might have a question at this point that in this equation, how do we know that the time that I'm computing, that value for t that I'm getting, is at a maximum height? So I'm going to just ask you itself, what do you think? How does this equation maintain assures that the time that I'm computing by this equation is the time for maximum height? Because there is no s, right? There is no distance or height variable in this equation. But still, I'm saying that you can use this equation to determine that time to reach that maximum height. Any idea? Just take a guess. Anyone? Look at the variables in the equation. Maybe you might get a hint. No idea? Okay, so I guess I'll just say it. So if you look at the variables in this equation, you have v, u, a, and t. Okay, a is telling you that there is gravity acting downward, so you put that value 9.8, so that is making sure of gravity. U is the initial velocity that you're giving to the ball. What is v? If I put in this equation v as 0, when will v be 0? It will be 0 at maximum height, right? So at maximum height, the velocity is 0. So when I put this v is equal to 0 in this equation, it makes sure that this equation is now set to be solved for maximum height, right? Where velocity is indeed 0. So you can write this as v minus u over a is equal to t, which is 0 minus 15 over minus 9.8. And that gives you around 1.5 seconds. Okay, so was that clear?
Yes, sir.
All right. Okay, so let's do another part. Okay, what else can you find? Okay, let's say that you want to find the let's say total time for the journey, right? Which just means that the ball was sitting over here, and what you did is you launched it. It went in the air, reached a maximum height, and then came back downwards and touched the ground again. So this the time that all of this takes to happen is what I want to compute. There is a very simple way that you can do this if you understand the physics of what is happening. Can you take a guess? How can I compute this total time? I'll give you a hint. We in one of the parts that we did previously, there is a hint in that, or at least we'll use that answer to solve this one, to find the total time of this entire journey. Any idea? Just take a guess. The reason I keep saying take a guess is I want to promote thinking. So I want you to think about the problem, try to visualize it, and see from whatever is given in the problem statement, how can you use those things to help you in getting to a conclusion. No idea? Okay, so what do we have? We want the total time, right? So we computed something that was related to time previously, and that was time to reach the maximum height. So if you look at this figure that I just drew, when is it reaching maximum height? At this point, right? It reaches maximum height at this point. What does that mean? That means that for this part of the journey, it takes 1.5 seconds. That's true, right? So when it changes its direction of motion, what is the force that is acting in the entirety of the situation? The only force that is acting on the system is the force of gravity in this direction. And it's not changing. When the ball was going up, it was downwards, g. When the ball is coming down, it is still downwards, g. So nothing, so as in the dynamically, the system is not really changing. It's just evolving, as in it's covering a trajectory, but nothing else is changing, which means that the time that it takes to reach maximum height, and if I multiply that by 2, why 2? Because it would be the same time that it would take to come back to the ground. Again, why? Because the force of gravity is the only force that is acting on the system, and it is constant throughout its journey, right? The weight of the ball does not change during this motion. So whatever time it took to reach this height is exactly the same time that it would take for the ball to go from the maximum height to the ground. So it should be 1.5 seconds, which means that the total time of flight, let's call it capital T, will be 2 times 1.5 seconds. Was that clear? The concept?
Yes, sir.
All right. Okay. Of course, there are multiple ways also in which you can do this problem. You can use by multiple ways. I just means just use any of the equations of motion, and you can solve this by using those as well. Right. So, okay. So let's. So this is well. Second problem. Now let's do another one. Let's go to the next page for that. Okay, so now suppose that here I have a ground, and there is some cliff or hill over here, and someone is standing on this. Suppose that the height from the ground level is 100 meters of this cliff, and the man is then launched from the cliff, right? He's launched from the top of the cliff, which is 100 meters high, and he's launched with a velocity of 20 meters per second. So the initial velocity is 20 meters per second. He's launched vertically upwards. Again, let's assume that air resistance is negligible. How do I find the first part? Is simple. How do I find the time to reach maximum height? How do I do that? Again, maximum height, what does that imply? Final velocity is 0. And now I have V, I have U, I have the acceleration that is acting on him. I have, what I want is, I want the time taken to reach the maximum height. So how can you find that? Suppose you don't have the maximum height, right? In this example, you don't have the maximum height. Can I use these variables to figure out the time?
Yes, sir.
Okay, so can you tell me which equation relates all of these?
Where V is equals to U plus AT.
U plus AT. So again, for maximum height, V is 0, so 0. And the initial velocity is 20, and the acceleration due to gravity is, again, if I take U as plus 20, it automatically assigns a negative sign to this one because it's in the opposite direction. So it will be minus 9.8 times T. And then you can just factor T out from this and get 2.0 seconds. Okay, so that's how you'll find the time taken to reach a certain maximum height. Now let's figure out this maximum height. Max height in two ways. Because we have a cliff, so let's say that you want this maximum height from top of the cliff. So the surface is a cliff in this case, and find the maximum height from the ground. So the heights that we want are the height from top of this cliff, let's call it HC, and the height that is reached from the ground, we can call it HG. So these are the two heights that we require. So how can I figure this out? Starting from the top of the cliff. Again, let's see what variables do we have. We have the initial velocity, we have the acceleration, or we have the final velocity at, because to reach maximum height, again, it is 0. And we want the maximum height, right? So which equation will I use that relates all of these? V squared?
UT.
Yeah. Sorry, which one are you saying?
Sorry, I thought there was time.
Okay, so time taken to reach maximum height, I can use that to find from the top of the cliff, right? Because he's launching the ball from he's launching himself really from the top of the cliff, right? So the time at this point before he launches himself is 0, and then as soon as he launches, time starts to tick, and so he reaches a maximum height, and the time for that is what we computed, right? 2 seconds from top of the cliff. But I cannot use this. I can use this time for this part A, top of the cliff, but I cannot use this time to calculate his height from the ground, right? Because this height that he's reaching, the maximum height that he's reaching, it's from the top of the cliff. So it's so still let's use an equation that does not involve time at all, right? Because for B part, we don't really have that time. So we can use V square minus U square is equal to 2AS. And again, here we have everything. V is 0, U is 15. Was it 15 or 20? I think it was 20. 20 squared is equal to 2 times minus 9.81 into S, right? And then this would give you S is 20.4 meters. Right? The mathematical steps are simple, right? You don't expect me to show you how can I factor S out and rearrange the equation and everything. That can be done, right? Or if you want me to, yeah, okay, all right. So this is the height, the maximum, the height from the top of the cliff. So in case, suppose if this was your reference point, as in this was 0, then from here to top of the cliff, the height is 20.4. So this height is 20.4 meters. Okay, so we have this. The next thing is from the ground, the maximum height reached from the ground. Just look at this figure carefully. How can I find that? It's straightforward.
Sir, it's going to be the double.
The total height, which is? So this is the total height will be? Yes.
Sir, 40.
It should be 40. How come?
Sir, I multiplied it with 2.
Okay. Why would you multiply it by 2? I mean, just give me a reasoning that you had in your mind doing that.
Sir, I thought it's going to be double of the height we find out.
Okay. But it should not be that, right? Because the height, this is the maximum height, right? The maximum height that is reached is not related really in any way from where I am launching this person. Wherever I'm launching this person from, I'm setting a reference point as 0, as in, suppose if I'm standing on the ground, for me, this where I'm standing is 0, and as I go up, I say I'm going 1 meters, I'm going 2 meters, and so on, right? You're starting from 0. So that does not depend from where am I launching this person from. So the maximum height from the ground could be, we know this one, right? So again, if you look at this part is known, but so is this one, right? Which is 100 meters. And once you combine this and this, it gives you this entire part, right? So you just add 120.4 to get the total height, which is the height from the ground. Is that clear? Okay. So HC plus. Sorry?
Sir, I didn't notice 100-meter.
Okay. So but now it's clear, right?
Yes, sir.
Okay. All right. So it's 120.4 meters. Okay. So this is part 2. What did we find? Let's see. Time, reach, and a maximum height. So what can I find now? Let's do another. Let's find. Okay. So yeah, we can find this thing. The man is launched, right? And he'll go up, and when he's coming down, he's going to cross this line again, right? This line that was initially where he was standing, he's going to cross that top of the cliff again as he comes down towards the ground. So let's say that you want to find that time when he comes back, when he's at this instant, right? When he's falling back down and he is at this instant, at this line. So what time, how much time will it take for him to come back to this, the same starting point where he started from, right? So how can we find that? So let's suppose that we are looking for time to reach cliff top again. Okay, so again, in this one, let's go back to the figure and let's see. So the person is launched and he goes up, right? He goes up to a maximum height. Suppose, okay, what I'll do is I'll draw it over here. The person is launched. Let's suppose the person is a spherical ball, right? We can do that. We can do whatever we want. And so he's launched upwards, and this is the cliff. He reaches a maximum height. Suppose this is the path. He's coming to the ground. This is the ground, and this is the cliff. So he reaches a maximum height over here. So this is the maximum height. And then he comes back down. The only force that is acting is the force of gravity downwards. So how long will he take to cross this point again? Remember, what we have is, we have the time, we just computed it, the time to reach this maximum height, right? This one. From the cliff. While he was standing on the cliff, from the top of the cliff, the time to reach that maximum height is known, right? We computed it at 2.0 seconds. I'm going to say that it would take the same amount of time for the person to come back to the same position where he was, at the same level, really, right? I want you to tell me, why is that so? Why would the time be the same?
Sir, because the only force acting on this is gravity.
Is gravity. So it's not nothing is changing. The force is constant throughout, so it will not change the system dynamically, which means that the time would be the same. So the time to reach the cliff top again is the time to reach maximum height plus the time to reach from the maximum height to the cliff top, right? So that should be 2 multiplied by 2.0 seconds, which is 4 seconds. So is that clear?
Yes, sir.
Okay, so right now, this was part 3. Let's do part 4, and let's again calculate the total time of the flight, right? Which is the time that, okay, he's launched upwards, he goes back down, crosses the cliff top, and reaches the ground. So how can I find that that time? Well, let's but for that, what you will need is, you will need the velocity, right? The final velocity with which he hits the ground. So let's compute that one first. Okay, so first let's compute the velocity just before he hits the ground. Okay, how can we find that one? So let's go back. What do we have? We have a lot of things now. We have the time to reach maximum height. We have the maximum heights as well. We have its initial velocity. We have acceleration. So let's just list what things that we have. We have initial velocity. We have the acceleration. We also have the height, and what we want is, we want the final velocity. Okay, so the question is, what value for s will I use? Now, I'm not going to ask you which equation will be used, because it's obvious now that the equation that relates all of this is 2as. We know v, u, a, these are pretty obvious. The thing that is not obvious is s. What s do I use? Should I use the maximum height that he reaches from top of the cliff, or from the ground, or just the height of the cliff? So what do you think? Which height should we use? Again, the question was to compute the velocity just before he hits the ground.